This is page 2 of evaluating limits algebraically. So we're just going to continue going through these practice problems on the second page. So for part C, first thing we do is we treat it like just evaluating a function at a point. So we just plug in 2 and for all the x's and see what we get. In this case, we get 20 over 4, which is 5. If we get a real number, then there's nothing that needs to be done more than that. We don't have any issues with holes or breaks. So if the function is continuous, then finding a limit is not going to feel any different than evaluating a function at a point. Okay, part D, limit as x approaches 2. So we plug in and we get 2 squared minus 4, which is 0. 0 over 4 is 0. So 0 is a real number, and so that's our answer. Now, I do want to make sure that we can distinguish between variations of zeros. There's, all these look kind of similar, but these subtle differences have a big impact in terms of how we interpret them. So first up is if you see 0 over 0, we call that indeterminate form. Okay, this means that there's a hole in the graph, that the limit exists, the point doesn't exist, but the limit still exists. So most of our problems that we're going to see is probably going to fall within this category, where it's going to be more than just plugging in, and we're going to have to figure out how to work around that hole in the graph. Now, if we get something like 10 over 0, 12 over 0, 5 over 0, that means that there's a vertical asymptote. Now, this does mean that not only does a point not exist, but the limit also does not exist. Okay, so this first instance, the point doesn't exist, but the limit does. Here, there's a vertical asymptote, so neither a point nor a limit exists. Now, this third instance, if the zero is up top and the non-zero is in the bottom, then we think of that as just 0. That's a real number. Limit exists, point exists. The graph is continuous through this point. So want to make sure that we are clear as to how to interpret these slight but important distinctions of the locations of 0. All right, these are practice problems here. So number 1, 2x squared minus x minus 3. First thing we do is we plug in for 1. So we get 2 minus 1 minus 3, negative 2 over 0, negative 2 over 0. This indicates that we don't have to go any further. This matches up with the fact that there's a vertical asymptote at 1. So right then and there, we can stop the problem and say that the limit does not exist. Right? Number 2, we plug in 3, and we get real number up above. We get non-zero below. 13 over 1 is just 13. That's our answer. There's no break in the graph, continuous function, so it's just like evaluating a function at a point. All right. Number 3, limit as x approaches negative 1 of x squared minus 1 over x plus 1. So here we get negative 1 minus 1, which is negative 2. I'm sorry, we get negative 1 squared, which is 1 minus 1 was 0. 0 over 0. Okay, so now we know that there's a hole in the graph. The limit does exist, but we have to dig a little deeper to figure out where that hole is. Okay, so we can do a little bit of work in this numerator. There's something hiding behind this x squared minus 1 that if we can get into factored form, we can identify common factors. And once we identify common factors, we can reduce and simplify and then reevaluate. So x squared minus 1, difference of squares, we can factor that to be x minus 1, x plus 1. We see a duplicate factor, numerator and denominator that we can remove. Once we remove, we have a clone version of this function, but this version doesn't have the hole in it. We're going to evaluate it like as if where that hole would be if it was there, if it was showing up because of this x plus 1, and the result we get is negative 2. All right, number 4. Plug in 1 and we get -3 over 0, -3 over 0. We see the placement of the 0 indicates that there is a vertical asymptote. Therefore, the limit does not exist. Okay, number 5. Plug in -3 to begin with, right? And so that's something that we have to be aware of. And this is also good for future sections as well, is that I think there's a tendency to look at a problem and kind of skip ahead and say, oh, look, this looks like I should be able to factor and reduce. I'm going to just jump ahead to that. But I want to keep reminding us, let's not skip that first step. If we can get into the habit of always evaluating, I think that will potentially save us from making some mistakes for future sections. So let's get into the habit of always evaluating first before we jump too far and thinking that we can factor. Now, it could be a factoring problem, but let's not assume that there's a hole. Let's always just plug in and see what results we get. And if we realize there's a hole, then we can take the second step of further evaluating and further algebraically cleaning up the expression. So we plug -3 in, we get 9 minus 3, which is 6 minus 6 is 0. So we do get 0 over 0. And there we know there's a hole. We know there are some factors that's hiding behind these terms that we can hopefully make them appear and allow us to see what can be reduced. So the numerator, we can factor this to be x plus 3, x minus 2. Denominator, difference of squares, we get x plus 3, x minus 3. We clean up the expression, we get x minus 2 over x minus 3, which is, I like to think of it as a clone version of this original expression without the hole. And now that there's no hole, we can reevaluate and we can identify where that hole was that before algebraically we weren't able to find. Okay? So we plug -3 in to the remaining expression. We get -5 over -6, which is 5 over 6. All right, finally, number 6, 5 minus x over x squared minus 25. We evaluate the expression. We get 0 over 0. We know there's a hole in the graph. And I'm going to do a little bit of work with the denominator, the x squared minus 25. Difference of squares, I'll make it x minus 5 and x plus 5. Now at this point, these are not perfect matches. But if we can do a little bit of rearranging with this 5 minus x, we should be able to get this 5 minus x to match this x minus 5. And the way I'm going to do that is I'm going to factor a -1 out. So if I factor a -1 out, I'm basically going to be changing the signs of what's inside the parentheses. So 5 becomes negative x becomes positive x. So if I factor a -1 out, I get x minus 5 to show up. Now I can see clearly that x minus 5 can be reduced. Don't forget about that -1 up in the numerator. Our reduced expression is -1 over x plus 5. Let's reevaluate and see where that hole is located. And we get -1 over 10, and that's our answer.